Okay, hello folks and welcome back. The next thing we're going to do is regression. This is a very powerful tool and it's very ubiquitous. You're going to run into regression in any kind of data analysis environment. And it's pretty tricky, it's pretty complex, and it's also kind of dangerous if you use it wrong because it's pretty actually easy to do in Excel. But there's a lot going on that we need to talk about. So what we're going to do first off is just kind of walk through what's going on and with regression, and then we'll talk about the terms and concepts that we need to understand in order to understand the regression results that we'll generate in Excel, and then we'll jump into Excel as per usual and then practice, including walking through most of the homework problems. And I'll leave, I think this time I'll leave 3 of the problems for you to do on your own. Okay, so first off, let's talk about what is regression, and we're talking about what's called OLS regression, ordinary least squares, the basic regression format you'll run into unless you get into really advanced level statistics. And basically all we're doing is applying line of best fit to a scatter plot of data. Something you probably have done in Excel. We've made scatter plots before in this class, and I think in a few of our homework exercises we put a regression line, or it's called a trend line in Excel. All regression really is doing is calculating that line. Okay, it's a linear relationship between the x variables and their corresponding y variables, such as we'd see in a scatter plot. Now, our linear form, so we're talking about linear relationships, our linear equation that we might be used to from just basic algebra, y equals mx plus b. This is called slope-intercept form, right? So we've got values of y on the vertical, they're based on values of x, and we have slope here and intercept. So we could have something like y equals 2x plus 10. We know the intercept is 10, and then for every x, y is 2 higher, starting at that intercept. So that would be 12, 2, 14, and on, and we would draw that line. Okay, that's basically what we're doing in regression. So we're going to change this up a little bit and use a slightly different format, but it's the same concept, linear equation. Okay, and the regression form is going to look like this. So this is going to be y, and we'll use capital Y this time. Okay, now instead of mx plus b, we're basically going to flip that around, and we're going to put a plus b x. Okay. Same format, we've just rearranged terms. Okay, so now this, the beta, or the b here, is the slope, and we'll call this from now on the coefficient on our x, and the a value here still is the intercept. Okay? We're doing exactly what you're used to with the linear equation format. We're just rearranging it a little bit, and we're going to work with this concept from now on in the context of regression. Okay, so we're talking about applying a line of best fit, and it's going to be linear. It's going to be defined by that formula y equals a plus bx. What does this mean, and how do we do that? Well, what we're going to do is minimize the sum of squared residuals about the regression line. Okay, what do we mean by that? Let me just try to show you really quick. So we've got a set of data. We've got x's and y's that are paired observations, and we've got our scatter plot. Okay, and we're going to jump into Excel pretty soon here to start working with this, but let's just think conceptually. We've got several points here. Okay, it might be a few outliers, but let's say we've got a scatter plot that looks something like this, right? And you can kind of visualize that there's a linear relationship that looks something like this. Okay, now we can't draw a straight line that perfectly connects all of those spots, but we can kind of draw it in the middle, so to speak. And that's what we mean by the sum of squared residuals about the regression line. So what we want to do, the residuals are going to be the vertical distance from each actual point to the regression line. So there's the residual for that point. Here's the residual for that point. There's a residual for that point. Residual. Okay, so we've got a residual for every point here. Some might have no residual. Some of them might be on the line, but most of them are going to have some residual, larger or smaller. Okay, this one's a big one. This one's here a little bit of an outlier. Okay, but we've got all these residuals, and some of them are higher than the regression line. So when we subtract the residual minus what we call the fitted y, the height of the regression line, Some of those are going to be positive if they're above the regression line. Some of them, though, are going to be negative if they're below the regression line. So we square them. Oops. I meant to draw a minus sign here. We square them in order to make them all positive. Squared makes those positive. Squared makes those positive. And then we sum them up. And basically what the computer's doing, and this is pretty complex algebra that we don't need to do, thank God, but what Excel's going to do for us is try basically every possible combination of lines and find the one that minimizes the sum of squared residuals about the regression line. And that kind of by definition means that we've got the line that fits this set of data the best. Okay. So that's what we're doing. We've got a scatter plot of data, whether we've got a positive relationship here, then Excel's going to fit that line and spit out a regression equation for us. Could also be a negative correlation. Okay, and Excel's going to put the line in there. The only difference is in our y equals ax plus b format, whether the slope here can be negative or positive depending on the kind of relationship we're looking at. Okay, now I want to stick with this theme of scatter plots here for a minute. When we are doing regressions, we always think in terms of scatter plots, and it's a very good practice to actually make a scatter plot before you even run your regression. And then actually there's a lot of other scatter plots we can look at while we're doing a regression or after we do a regression, and we might get into a little bit of that later on. We'll look at scatter plots of residuals and things like that, but scatter plots is the visualization of what we're doing in the regression. Okay, and in simple regression, it's really evident when you only have one x variable. Eventually here we'll get into multiple x variables and we can't really do a scatter plot, but we want to think in terms of the scatter plot. Just looking at the scatter plot, some professors I had in graduate school, they said, well, you can just look at the scatter plot and you can visualize where that line would go, and they call that the optical least squares method as opposed to the ordinary least squares. So OLS, that's just kind of what you get by looking at the data, and you can see that relationship often. Sometimes you can't, and there still is a meaningful relationship, but most of the time it's pretty evident in the scatter plot. And in Excel, and we'll do this here, when we create a scatter plot with just with a paired set of x and y data, you put that trend line in, and you can have Excel show the equation, and for a simple just one x and one y, that is a regression equation, and I think we're going to have a problem where we prove that. Before we do anything in Excel, we've got to go through some terminology. And first off, we want to talk about the two different kinds of variables we're working with in a regression. Okay, first off, we have the dependent variable, what we're explaining or predicting. And this is the one that changes based on the values we feed in of the independent variables. It's the y variable. It's also known as the left-hand side of the regression equation. Y equals a plus b times x. Okay. This is on the left-hand side of the equation. These ones are on the right-hand side. So it's I like the terminology of left-hand versus right-hand, dependent versus independent. It's also used. The book says this can also be called the response variable or the target variable, and that's as opposed to the independent variables, which are the right-hand. Okay, these are the x's. I'll also refer to these as the x's, and this is the y. Okay, so the x's, the explanatory variables, the predictor variables, the values of x change, and according to the b and the alpha parameters, the value of y is expected to change in a certain amount. Okay, and that actually brings us to a point where we're ready to jump in Excel and start playing with regressions. And I want to go ahead and work through one of the big textbook examples. And by the way, while I'm setting this up, let me say that this book is an excellent book, and if you've read through the chapters 10 and the sections I have signed of chapter 11, if you find that challenging, well, that's just because regression is challenging, especially if you haven't worked much with it before. If you haven't worked much with statistics, regression is tough, especially once you get into the more complex issues. This book here, though, I think does an excellent job, and that's from having a little bit of experience with different teaching materials. So I will tell you, we can't do much better than the book we have. But it is always ideal to actually work in practice, and it's actually quite easy to do in Excel. So let's jump into Excel, and the first example 10.1 here, which I'm finding on page 467 if you want to follow along in the book, is about the sales versus promotions at Pharmex. It's a hypothetical drugstore company. And it says, to see how effective its advertising and other promotional activities are, the company has collected data from 50 randomly selected metropolitan regions. In each region, it has compared its own promotional expenditures and sales to those of the leading competitor in the region over the past year. There are two variables. Promote, and that says Pharmex's promotional expenditures as a percentage of those of the leading competitor. And then sales. That's Pharmex's sales as a percentage of those of the leading competitor. Okay, so we have in that basic idea that there's a relationship between promotions and sales. The more they spend on promotions, arguably the more sales they will have. Let's get rid of this junk. That's obvious, but we want to kind of specify that relationship rather than just guessing at it. So what we're going to do, and at the bottom of 467, it says to objective, use a scatter plot to examine the relationship between promotional expenses and sales at Pharmex. Remember how to do a scatter plot. I'm just going to select all the data, including the column headers, and we're going to go insert scatter plot. Let's add axis titles, and let me make sure that we've got what we want to have is the left-hand variable, or the y, the dependent variable on the vertical. So I just want to check and see. Okay, so I've got my b's are my x values and my c's are my y values. So that's correct. Okay, so I can title this down here. This is the promotion index of expenditure, so I'll call it that. And then this is the sales index, the index of sales. And to visualize our scatter plot better, let's format the axis to where we chop off that irrelevant range down there. Let's start it at 60 on the horizontal, and then on the vertical, let's start it at 60. This will be exactly how the book has it. Okay, so now we're matching up with the book. We might retitle it to Sales versus Promote. Okay, so that's exactly what the book has now. And as the book says, this scatter plot indicates that there is indeed a positive relationship between promote and sales. The points tend to rise from bottom left to top right. But the relationship is not perfect. If it were perfect, a given value of promote would prescribe the value of sales exactly. Clearly, this is not the case. For example, there are 5 regions with promotional values of 96. You can see those right here. 1, 2, 3, 4, 5. But all of them have different sales values. So the scatter plot indicates that while the variable promote is helpful for predicting sales, it does not lead to perfect predictions. Okay. Now, in the book, they're using the thing called stat tools, which is a add-on package that does a few things for you, but we can do everything we need to do in just regular old Excel. And what we want to do is run a correlation between sales and promote. And we've done this, right? Array 1, and then array 2, using Control Shift down. 0.673, the book is rounding a little bit, so let's match them. Okay, so there's my correlation. Okay, the correlation is 0.673. For now, just note that it is positive and its magnitude is moderately large. We'll say more about correlations in the next session. Okay, so that's all the book does. I know that's really simple, but let me do one more thing, because I can make the connection here. We can kind of make the leap between correlation and scatter plots, which we already hopefully know a lot about, and regression. So I'm going to now click on my data again, and I'm going to click on this little plus sign for some chart elements, and I'm going to select trend line, and I'm going to select this extra arrow here to do a linear trend line. Whoops, and more options. I want to show the equation on chart. Okay, that right there is my regression equation. Let me make this a little larger and highlight it so we can read it. There's my regression equation. Okay, it's in that familiar form that I was talking about earlier. It's in that form we talked about. Y equals A plus BX. Okay, there's our intercept, 25.112. If we extended that regression line, it would indeed have an intercept about here, 25. And then the slope of it is 0.7, just under 1. So there's almost a 1-to-1 relationship. And what that means, we'll talk about this more later, but what that means is that a 1 unit increase in x, so if the promote index went up by 1 point, we would expect the y to go up by 0.76 points. So we're actually doing a regression there when we have Excel insert the trend line. That's what the trend line is. That's an OLS regression. You can also probably heard it referred to as a line of best fit. Okay, that's exactly what we're doing with regression. So I hope we have a pretty good idea of what regression's doing. Okay, so now we're ready to move on and learn a little bit more about how regression works, and then we'll be ready to do full-blown regressions and really understand what we're doing. Okay, but first let me talk a little bit more about the kind of variables that we'll be using, that we could possibly use and we will be using on the right-hand side of the regression setup. So far, and in that trend line we just did, which is technically a regression, we're using numerical continuous variables, and we don't need any further explanation on those. We know that they can take any value, and they're just regular old numbers. Okay, but the neat thing about regression is that we can also regress on categorical variables, or we can transform variables that, if they aren't linear, to make them linear often, so linear regression can apply. Okay, so categorical variables, they take a discrete range of values, like male versus female, or whether you're a graduate or an undergraduate, or a non-college student. You know, that could take 3 values maybe. We could use events that happened over time, whether that was in 1 out of 12 months. So you'd have 12 categorical variables there, or 4 quarters of the year. Okay, there's a whole lot of different categorical variables of interest, and in order to use them in a regression, we have to somehow convert them to numbers. Well, what we'll do is we'll just code them, and this is called dummy variables, to a value that represents the category. So with male and female, we can set the value equal to 0 or 1. Okay, if we have more than 2 categories, which we often would, we could just set the value to 0, 1, 2, 3, etc., depending on how many categories we have. So if we have data on the sex of respondents or people that we're studying, and we think that might be relevant to as an explanatory variable, and we want to include it in the regression, we can't put male and female in there. Those are words. We have to regress on numbers. But we can convert it to a number by setting it equal to 1 or 0. So we'll set it up as either male or female, and then if the value is 1, it equals what the column is. So we'll put the heading female in the column. We think the female variable is the relevant one. Of course, if there's only 2 variables, if there's only 2 categories, male and female, of course they're both kind of automatically relevant. But anyway, we can set it up either way. Female, so you set it equal to 1 if female, 0 if male. Or if we label it male, we do the opposite. 1 if male, 0 if female. Okay, and then we'll basically be saying that if we get a coefficient on that variable in the regression, that's the difference in our estimate for one observation being female versus male. This will make more sense when we get into some examples if it doesn't already. And one other thing I want to mention, the book talks a lot about this, and it's very useful, but I'm going to just kind of skim it because I don't want to get bogged down too much in some other math. I want to focus on just learning about regressions. But it is important to note our ability to do what's called nonlinear transformation with variables that aren't quite linear, because with least squares regression, we're doing linear regression, we need to have pretty much linear underlying relationships in our data, and sometimes we don't. So what do we do if we have data that looks curved? For example, let's say that if we did a scatter plot, this is our scatter plot of x's and y's, and it looks something like this. Okay, so there's no, we could fit a line to that, but it wouldn't be a good fit. The best fit would be an equation that looked like this, which would be some kind of power equation. That would be some kind of, that would be like y equals x to the 1/2 or something like that. Okay, so what we could do is, instead of taking the y values, if we took the logarithm of them, that would probably straighten this out to make it look more linear. Okay, and let me show you an example. Okay, and just quickly to illustrate an example, I just grabbed some data I have from a macroeconomics problem. It's a really basic model of economic growth. And what we have here is total output of the economy growing at a diminishing rate. And let me just show you that in chart form. So you can see that that's not quite linear. Okay, that grows much faster down here for low values of x than it does for high values of x. But if I go ahead here and take the let's do the natural log first, ln of output, and that's just equals ln of that value. And if I fill that all the way, and then if I graph that, and now what I want to do is select both of those and compare them side by side, and you'll see the red one, which is my log, is much flatter. Okay, so when I took the natural log of the data, it tends to squish down those differences because, and I can also do a log base 10 if you're familiar with more familiar with those than with natural log. Same concept. Let me just move my chart up here. Let's do the log base 10 of output, and that's just log 10. Okay, and then let's graph all of those side by side. And that's my green line. It does about the same thing. Maybe makes it even a little bit flatter because what we're doing there, what the log does is says 10 to the x equals this value. That's going to be those values are going to be much closer together than these values are when we take 10 to the x equals that value. So 10 to the x for the values around, when we go from 27.9, let's go from 20 to 30. Okay, when we go from 20 to 30, the log only goes from 1.3 to about 1.5. Yeah, 1.5. So when y goes from 20 to 30, the log of y only goes from 1.3 to 1.5. So there's much less variation there, and it makes it flatter, more like a straight line. Okay, so I won't get much more into this logarithmic transformations, but I just want you to be aware of that as a tool to squash out the more curved kinds of data and to then make the data more amenable to linear regression. Okay, so now let's move along and talk about interpreting regression output. There's a lot of things when we run a regression. We're going to get a whole chunk of output and a lot of different elements of that we have to understand in order to make sense of what this regression is telling us, and really indeed whether it's a good regression or not, whether the results are strong enough for us to make some inferences about or not. Okay, so I'm going to run through all these concepts right now, and then I'll post the slides here so you can kind of reference this if you need to, or you can reference the book, but we'll really start to understand these once we do a regression and look at the output within Excel. Okay, so first off, there's the standard error of the estimate, which is indicated by S sub E. And what this is basically it's just the standard deviation of the regression residuals. And remember what the residuals are. The residuals are if that's our regression line, and here's the actual data here, the residuals are these distances, these vertical distances between the y value and the regression line. So we've got a set of residuals, and they've got a distribution, and we can calculate the standard deviation of them. And that's what we call the standard error of the estimate. Now, just kind of thinking visually here, here's y, here's x, our regression equation, y equals a plus bx. What are we looking for in a standard error of estimate? Well, the better the line fits, the smaller these residuals are, and then probably the more tightly clustered, so they would have a smaller standard deviation, so the standard error would be smaller. So we're looking at smaller standard errors of estimate, give us a tighter fit, and a better regression result. Okay, then we compare the standard error to the standard deviation of y about its mean, and that kind of helps us understand how good of a job the regression is doing for us. If that standard error is less than the standard deviation of y, that means what the regression is doing is tightening up the variability of y versus what it kind of was on its own. To show you what I mean by that, I know this is kind of tricky to understand, but think about, we've got just the y's now. And there's this line here is in a regression line. This is the mean of the y's. And the individual y's are dispersed around that. And then we can look at that distribution and calculate the means. We've calculated the mean, the standard deviation. What we're doing with the standard error is kind of the same concept, but instead of this over here is looking at the distribution of the actual y's, the observations of y about their mean. This over here, the standard error, is looking at the distribution of the residuals of y about the regression line. Okay, so we've got all of our values of y scattered around here like this, and we're looking at these residuals. So if the standard error, that means the dispersion of the y's about our regression line, is less than this, just the standard deviation of y, the regression is actually fitting the y's better than its own mean does. So basically that means the regression is doing a good job for us. So the basic rule, though, if you didn't understand that, that's okay. We're just looking for smaller standard errors are better. Okay, and you could also kind of think of the standard error tells you how far off on average the fitted value of the regression line is from its residuals. We typically have the residuals normally distributed, so the empirical rules apply. The standard error of the estimate means that 68% of the fitted estimates are within one standard error. Okay, so this gives us a range in which most of the fitted estimates are going to lie relative to the actual y's. Okay, next is R-square, and R-square might be the single most important regression output. That's kind of the overall indicator of how good our regression is. So it's important to talk about this for a minute. It's really just the square of the correlation coefficient if we're doing a simple regression where we only have one x and one y. But you can think of it as that for right now. So back to Excel here, where we started with the scatter plot, and we had Excel calculate the regression equation, trend line equation as it's called. It's really a regression equation. And then I calculated the correlation up here. Well, we can calculate the R-square by simply squaring that. So that's our R-square. It's 0.452 in this situation. Okay, here's the formula for general regressions. This would include multiple regressions, which we'll get into here pretty soon. So it's 1 minus the sum of squared residuals. And this equation would really look like this. I wrote out the words so we can think out the logic, but I can pencil in here the notation. Sum of all the residuals, those are denoted E, EI's squared, divided by the sum of squared deviations of y from its average, from its mean. So the y's, yi, minus y bar squared. Okay, so what's going on there? Well, notice that smaller residuals relative to the dispersion of y make r squared closer to 1, and it can be 1, right? So, if we have smaller squared residuals, let's start off by saying that the numerator here is 10. Now let's start off saying the numerator is 100 and the denominator is 100. Well, then that's 1, and 1 minus 1 is 0. That would be the lowest possible r squared. But the smaller this numerator gets, meaning the smaller the sum of squared residuals, which means the less distant the residuals are from the trend line or the regression line. So if this is now 50 over 100, this is 0.5, so our r squared would be 0.5. If this is only 10, if our sum of squared residuals is really small relative to the squared deviations of y, then this is 0.1, and our r squared is 1 minus 0.1, 0.9, and 0.9 would be a really nice r squared. Basically, the higher r squared, the smaller the residuals are relative to the deviation of y. That kind of gets back to this concept I was talking about here, where if the standard error is less than the standard deviation of y. Okay, and that concept is confirmed by having a larger r squared. Larger r squared. Now, if none of that stuff clicked with you, hey, I understand. It's taken me many years to understand regressions, and I'm still not very far along. So I understand. But if you need to just codify this, just say this: larger r squared is better. Just like smaller standard error is better, larger r squared is better. R squared can be thought of as the percent of variation in the y's explained by the variation in x's, or it's a shorthand way of thinking about what's the explanatory power of our regression. Closer to 100% or the closer to 1, the better. Okay, multiple r, closely related to r square. This would be the correlation between actual y's and the fitted y's, the estimated y's. And this is just the square root of r square. Okay, what does this mean? In a simple regression, r is the same as the basic correlation coefficient, and in this example we can go back and calculate that. R equals square root of r squared, and of course it's going to equal the correlation coefficient because we calculated r squared on the basis of the correlation coefficient. Okay, then let me just run that exercise to confirm that in our mind. What this does is tells us the degree of correlation between x and y. Yeah, basic correlation coefficient. And like r square, larger r the better. It goes right along with r square. Larger r's tell us that we have a really good fit with our regression line, and it tells us that the variation in the x's explains more the variation in the y's. Okay, so that covers the theory of regression. We'll take a break now, and then we'll come back and do some practice problems in homework 6.